Thank you.
The original need for the Poppet to be redesigned came when Parker wanted to consolidate parts and also create a more cost-effective part, an injection molded part, to replace their current brass design. Their first prototype was found to have reduced flow, and so the goal of our project is to create an injection molded Poppet to replace the brass design that matches or improves on the flow rate and other functional characteristics. The methods of analysis that we use through our testing include computational fluid analysis using ANSYS Fluent, finite element analysis using Autodesk Inventor, physical testing that was conducted at Parker Hannifin, and numerical calculations that were done by hand and using Microsoft Excel.
Since every prototype valve component is compatible with one another, it was important that we came up with a configuration naming system. So the prototype naming convention that we use throughout the project consists of two different prototype model numbers. The first number called out refers to the stem model number, and the second number called out refers to the valve base and facing model numbers, because each iteration of the valve base and facing correspond to one another. In these diagrams, you can see an exploded view of the prototype Poppet valve components, as well as the geometric features of each component. So the facing is a rubber component that contacts the insert and allows the valve to seal in the closed position. The stem contacts the orifice insert, and that controls the opening and closing of the valve. The valve base is the housing for the facing and the stem, and that forms the internal chamber with a piston that allows secondary pressure to balance the system. The stem clips secure the facing and stem to the valve base, and the stem skirt provides the surface that allows the facing to be secured to the valve base, and the stem port allows secondary pressure to build in the valve base internal chamber. And you can see valve lift on this diagram is the vertical distance between the fully open and closed positions. Several theories determine the rationale behind our first round of prototypes. We believe that the addition of a stem skirt was going to drastically inhibit flow through the regulator. We also believe that the area formed between the valve base and the cage would cause a flow restriction. So with these theories in mind, we designed several prototypes that would be able to isolate the effect that each of these variables had on the attainable flow rate. And these prototypes can be seen below with differing geometries. The conclusions we arrived at from physical testing of our first round of prototypes determine the rationale behind our second round of prototypes. We found that the skirt geometry and the valve base diameter both had no inherent effect on the maximum attainable flow rate or the airflow characteristics. So the next variable that we decided to investigate was the effect that the valve lift had on airflow. And this was done by creating prototypes that had larger stems, which would allow for a greater maximum valve lift. We also hypothesized that the stem diameter may play an important role in determining the attainable flow rate. However, if we wanted to design extra prototypes to investigate this, they would have to be made, or they wouldn't be made in time to get any tests on this variable. So we decided to make the diameter of these extended stems equal to that of the brass stem, which is proven to work.
Okay, so with the prototypes that Nick made in the Autodesk Inventor, I took those and replaced them with the brass Poppet and the regulator using SpaceClaim, which is ANSYS's CAD program. With the new prototypes inserted, I was able to generate air volume models, basically to represent the behavior of the fluid through the regulator. With the models, put them through the meshing process. One of the biggest limitations for this was the element sizing. The amount of elements really contributed to more realistic flow rate values, which I'm going to talk about later. But after the meshing process, put the models through the ANSYS Fluent, set specific parameters like the inlet outlet pressure and ideal gas quantity as well. And at the end of the ANSYS Fluent process, collection and organization of flow data. I'm going to talk about that in the next slide here. So the four main things, the four main data categories were pressure contour, velocity magnitude, turbulence intensity, and volumetric flow rate. Pressure contour, just to show how the main function of the regulator, showing how the pressure decreases from the inlet to the outlet. Velocity magnitude, seeing how the velocity changes around different geometries. Kind of going in hand with that. The turbulence intensity as well. And then finally, the volumetric flow rate, which is the main finding. Here is a few snips from the ANSYS. This is the MK 3.13 prototype. Total pressure contour, velocity magnitude contour, and turbulence intensity contour. And then a final snip of the volumetric flow rate. This is a grand total of all the prototypes I tested in ANSYS. This CFD data allowed for a basis of understanding for various Poppet parts and features. Although these are not closely related to the physical testing data, trends can be seen to benchmark the different Poppet designs prior to physical testing. However, the final four prototypes had a direct correlation with the physical testing data and can be noticed in the following sections.
Using FEA software, we also calculated the safety factor for each of our prototypes. The safety factor is essentially just a ratio of the ultimate strength over the maximum von Mises stress that a component will see. Our prototypes ranged in safety factors from 1.7 to 2.32, which were all an anticipated decrease from the brass safety factor of 3.35, which makes sense because we're transitioning from a metal to an injection molded plastic. Although in our testing we did not experience any failures, and further endurance testing will be required for validation of our prototypes going forward. So we conducted compression analysis using FEA software and physical testing as well. This was done because we anticipated the rubber facing would drastically increase poppet compression. The FEA software predicted that the maximum compression of the injection molded poppet would range from 0.1 to 0.15 millimeters, whereas the brass poppet would yield almost no compression. Our physical results actually confirm this, where the injection molded poppets compressed to 0.13 millimeters and then beyond close to 0.2 millimeters, whereas the brass poppet compressed almost none. We could not actually measure that by hand. And this just substantiated the thinking that the compression needed to be taken into account when designing for an optimum flow rate. The testing method that we used for our physical testing was in accordance to ISO 6953-2. This is an industry standard test specification that's used to compare products with competitors, so there's a baseline for comparison. This uses an inlet pressure of 145 psi and beginning set secondary pressures of approximately 116 psi, 91 psi, 58 psi, and 36 psi. And the test essentially opens the secondary pressure to atmosphere to allow pressure to flow to the point that the poppet reaches a maximum opening and maximum flow, and then it closes that opening in order to close the poppet. So before we show you our physical testing results, we wanted to show you a timeline of our physical testing just to give you an idea of how things transpired. So our benchmark testing was conducted on July 15th. This was done with the current poppet design, the brass design, and Parker's original injection molded prototype. Our first round of prototype testing was conducted on November 5th. The focus of this was on the stem skirt and valve-based geometry's effect on flow rate. We learned that there is still reduced flow and there was no improvement across the prototypes, which meant that the stroke or valve lift was the limitation for flow. We did another round of testing with the first round of prototypes we had made and increased the stroke by reducing internal geometries. This confirmed that increasing the stroke increases the flow rate. And we did a final round of testing with the second round of prototypes that we had made with extended stems. This was done on December 3rd and confirmed that increasing the stroke could provide a flow rate equal to or greater than the brass poppet, but also caused functional issues, which we'll talk about in coming slides. Here are the benchmark testing results for the brass poppet design. First of all, looking at the figure in the top right-hand corner, you can see how to read these graphs a little bit. where secondary pressure is on the y-axis and flow rate is on the x-axis. As the poppet's opened, secondary pressure will be lost and flow rate will increase across a good operating range until it hits a choked flow region, and then the poppet will begin to shut again. And as the poppet is shutting, the flow rate will decrease while pressure increases at a slightly higher rate than it was when the poppet was opening. This is called a hysteresis and is typical in mechanical devices and caused by frictional forces within the system. The brass poppet design was found to reach a maximum flow of 208 SCFM in the choked flow region and had an optimal operating range up to 160 SCFM. Here are the maximum flow rates for all of our prototypes throughout physical testing, and while the maximum flow rate doesn't necessarily indicate the best operating range, it's a good benchmark for flow capacity. What we've done here is separate each round of testing by these white bars in the graph. So the final prototypes are on the very top. The first round retesting is below that. The first round original testing is below that, and the benchmark testing is on the very bottom. What we found throughout our testing was that 2 of our final designs were able to achieve similar or surpass the flow rate that the brass poppet was able to achieve, but those induced functional failures at zero pressure conditions, where the 3.1 stem immediately regulated to 25 psi, and the 3.3 stem could not relieve pressure below 5 psi. And here are some flow graphs that we collected throughout our testing. The top left shows the desired flow of the brass poppet design. The top right shows our best of the first prototypes, the Mark 33, which still exhibited reduced flow. You can tell because it's dropping secondary pressure at a lower flow rate. The bottom left shows the 3.1 stem, which had the overextended stem and had functional issues, but it did achieve improved flow of 220 SCFM compared to brass's 208 SCFM. The bottom right shows the 3.3 extended stem design, which was slightly shorter than the 3.1 stem design, and this achieved almost exactly the same flow as the brass poppet design. And this graph compares the flow graphs of the brass poppet to the final prototypes that we had made. The brass poppet is in yellow, the 3.1 stem is in red, and the 3.3 stem is in blue. The biggest takeaways for us was that the stroke needs to be extended between the values seen with the 3.1 and 3.3 stems, and that the functional failure at zero pressure conditions needed to be addressed with other internal geometrical changes within the regulator, which will be addressed later.
For our numerical analysis, we modeled the system as a steady flow system with a constant inlet area and pressure and a variable secondary pressure, with the area being that of the valve curtain area seen on the side. Using Bernoulli's equation, we were able to obtain a modified equation to solve for the effective area, and that's seen in equation 3. And since we know the equation for the area of the valve curtain, we were able to derive an equation for the valve lift as shown in equation 4. And using these equations, we created a plot to determine the ideal valve lift with a known flow rate and secondary pressure. And we also plugged values from the physical testing into these equations and created plots of the valve lift as the flow rate increased for several different valve types. And you can see from this chart that the configuration with the greatest valve lift exhibited the highest maximum flow. After our second round of physical testing, we found that 2 of our final prototypes functioned similar to or better than the brass valve in terms of flow rate characteristics. So first, Mark 3.13 showed greater maximum flow than the brass, and the pressure versus flow rate graph exceeded satisfactory characteristics. However, it was unable to regulate below 25 psi at the zero pressure condition, and this is because the poppet stem is contacting the diaphragm and the adjusting spring early, which creates a force that causes the regulator to balance at 25 psi. Second, the Mark 3.32 achieved similar max flow compared to the brass, while also exhibiting satisfactory characteristics in the pressure versus flow rate graph. However, this configuration wasn't able to relieve below 5 psi when the regulator wasn't used in its recommended orientation. And this is because the extended stem is too long, which creates a tensile force in the diaphragm, which in conjunction with the weight of the adjusting spring is enough to prevent 5 psi from lifting the diaphragm and relieving through the bonnet.
We concluded that the valve lift was ultimately limiting the flow and that increasing the maximum valve lift would increase the maximum flow rate. However, our testing showed that we would need to modify internal components in conjunction with the new Poppet designs in order to match the flow without the functional issues that we were seeing. We also found that valve bases 2 and 3 are both viable for this design, as valve base 2, even though it was larger, did not restrict flow at all. And we also concluded that compression must be taken into consideration when designing this injection molded Poppet. Before we get to our final recommendations, I wanted to bring up the valve lift limitations of the internal geometry and explain them a little bit. Firstly, the valve base to cage distance was found to never limit the valve lift. Secondly, the piston height was also decreased at the beginning of testing in order to remove the Poppet to piston limitation. And the ultimate limitation to the valve lift is the distance between the diaphragm insert and the regulator insert, which is shown in this picture to the right. The valve lift or stroke is ultimately dictated by the stem length and the geometry between that diaphragm insert and the regulator insert. So a couple things could be done using the current components of the regulator in order to maximize the room within it and correct the functional issues that we're seeing. Some recommendations that we have include raising the neutral height of the Poppet stem seat or the green piece that is sitting inside the purple diaphragm insert, and that would accommodate an extended stem. Two other recommendations we have are removing material from the diaphragm insert and removing material from the aspirator face. And this was actually done in prototype retesting and was found to increase flow when we did that. Our final recommendation would be to incorporate a rolling diaphragm rather than the current design. This would eliminate tensile and frictional forces, and additional benefit would be to improve the hysteresis of the flow graph. Here's a list of references for this presentation. Finally, we'd like to thank our industry and faculty mentors who have helped us throughout this entire project. Adam Armstrong, Ho-Sung Lee, Jason Sutter, and Yufeng Chi, as well as our families and friends who have also supported us along the way. Also, thank you to everybody who's taken interest in this presentation and our senior design project, and we'll take any questions at this time.
Okay, thank you very much, presenters. So this is a time to ask a question, please. You can either, let's say, type your question on the chat room, or you can unmute your mic and ask the question directly. Okay. At the meantime, guys, can you tell me what is the hardest part, let's say, doing this project?
I don't know if it's necessarily the hardest, but I would say one of the largest challenges and frustrations was using our own equipment to get all of our CAD models and run all of our CFD data, not having access to all the school's resources.
I agree.
Okay, thank you. So any other questions from the audience, please?
Yeah. Hey, this is Nick Larson. Hey, Jake, I missed. Did you guys use 3D printing to get your prototypes for this?
No, we submitted these to the tool room and had them manufactured.
Okay.
There. Yep.
You just machined out of plastic stock?
That was Delrin.
Yep.
Yeah, and we had actually considered 3D printing, but weren't able to find it in time in the tool room. Just ended up being more convenient for us.
Okay. That's an excellent. You did a lot of iterations there. Those are really good flow graphs.
Thanks, Nick.
So any other questions to our presenters?
And recommended orientation of the regulator. I've seen them recommended in two ways, facing straight down and facing straight up, according to the the adjusting knob. In combos, they usually are straight down to give you a flat surface up top. Which orientation was recommended?
We were referencing straight down, and this was just because of the adjusting spring weight that Nick had mentioned in his slide. That was just shown to relieve the 5 psi that was unable to relieve in the 3.3 stem that we had mentioned.
Okay, okay. There's one question coming up on the chat room, guys. So the question is, okay.
I can see that there.
Okay.
I think the biggest thing for me was submitting our first prototypes. I think we would have started earlier on getting our first prototypes designed, because once we had those, we learned a lot really fast, and just were able to gain a lot of data and a lot of knowledge. And I think we could have made the internal geometry changes with the time if we had gotten those submitted earlier. So that was the biggest thing for me, was just starting the physical testing process earlier.
For me, if I could do anything different, it would be like I showed in the slides, we had 2 different rounds of prototypes to test several variables. And this is just because we felt strongly that certain variables would restrict the flow more than others. And I think that was naive of us. I think we should have designed prototypes right away to test every different variable in the valve geometry. And I think we would have arrived at our conclusions a lot sooner and had more time to work on another prototype maybe.
Okay, guys, thank you very much for the presentation. We'll conclude this session here. The next session will be at 11:30. Thank you, everybody, and please come back or tune on.